In this video, I'm going to be showing you how to solve the Thomas Jefferson CTF problem, Secure Secrets, which is a binary exploitation problem that's going to involve a format string exploit where we use the global offset table to redirect program execution to a secret function hidden within the binary. So, starting this problem, they give you a 32-bit ELF binary, which means that Windows subsystem for Linux isn't going to cut it, and we're going to have to use a VM or be on actual Linux that can support 32-bit binaries. So I'm over my Kali VM, and I've downloaded that file here as secure. And if we look at what it is, we can see it's a 32-bit Linux executable. And the first step generally now is to do some behavioral analysis on the program. So we just run it and see how it works. So first thing I usually check for if I'm trying to break it is buffer overflow. Didn't look like I seg faulted or anything truly interesting happened. And the second thing is format strings. Skipping right to the point, what I found after some playing around was that the password is just used as a password, and then the message is treated as a format string when it's printed out if you get the right password, and you can leak data off the stack. So the next question is, where is the password stored? Is it on the stack, and is it usable as pointers for that format string, or is it going to be in the heap and we're going to have a problem? So the way to check this is without using GDB, just to see how many characters we can put in a password. It turns out to be 14. Then leak off the stack as many values as we can until we start to see the data that we put in. It turns out that it's the 11th index on the stack where that data starts. You can see the A's as hex 41s right there. So quick shortcut with format strings is that if you use the $sign operator, we can access directly the 11th part, the 11th index on the stack. So now we know we have an arbitrary pointer which we can create on the stack and a format string exploit that means we can write arbitrary data wherever we would like. But we can also leak arbitrary data. So the question becomes, do we want to redirect program execution at all, or do we just want to leak data? And if we do want to redirect program execution, where do we want to go? In order to answer this question, we're going to have to figure out what kind of data is in the binary. So my first thought was to see, is the data on the server in their binary that might be slightly different than our binary, such as, is there a redacted flag in the binary? So the first thing I did was do a strings and look for TJCTF, or they've been using redacted in all caps, or maybe flag. Flag.text. That's not looking good for my case because the fact that they have a flag.text string in there leads me to believe that they're going to load the flag at runtime or on a function call. If we're lucky, the flag's loaded at runtime from that text file, and I can just leak it from wherever I am without having to redirect execution. So my next step was to check about whether I could do that. So we just open the binary in GDB, then look for functions. So we got main, and then get secret, set message, get message. So get secret looks interesting. Let's take a look at that. Just disassemble get secret. And yes, I know I didn't change the assembly flavor. I haven't set up my GDB init file yet. But if we look here, we can see this calls an fopen. So the data for the flag is probably not loaded into memory until that function's called, which means leaking memory is out. We're going to have to redirect execution to run this function. Now, how do we redirect execution to run that function? Well, there's this wonderful thing called the global offset table, which the procedural linkage table goes to in order to find out where to make a libc function call. And we can overwrite entries of the GOT at runtime because they need to be edited at runtime. The next logical question is, what function's GOT do we want to overwrite to execute our secret function? Well, the main function ends with a call to exit at the procedural linkage table. So if we overwrite that GOT address, that should work fine. In order to do this with format strings, we're going to need to use the %n format specifier which writes the number of already printed characters to the location referenced by a pointer passed as a stack argument. So we're going to use the fact that we control the 11th entry on the stack with the password to create a pointer to an arbitrary location, in this case the GOT address that we want to overwrite to change the execution and run the getSecret function. And then we're going to write the value we want into that location. So this would be possible to write the whole value with %n, which writes a 4-byte integer, but we don't have to, because if we go back in here into the binary and we look at the GOT address, let me just find exit and then disassemble. And we look at where getSecret is, we can see the start of these hex values, the 0804 bit, is the same in both the location of getSecret and the value held in the GOT entry. So we only really need to write the least significant 2 bytes. Now I've done this 2 different ways here. In my old script, I did 1 write of 2 bytes, which required printing about 34,000 whitespace characters using %, then that number of characters I needed to print, which would be the value that I'm writing into that location, x. So it's just getting value from the stack, printing that, but padding it with so much. And as a result of padding it, that allows me to control how many characters are written, which allows me to control what %n will write. Then I'm writing %hn to the 11th entry with the $11 sign, but it writes 2 bytes instead of 4 because of the h. So this works perfectly fine. All I had to do was open up Python and find out the value in decimal of hex 8713, which is 34579. So that's the number of whitespace characters I'm going to print. And then we write that to the location of the 11th entry. And we also have to package the address of GOT for exit. So we just put one of those, and then the command to write via format string, and then the address again because that's the password to get the exploit to run. And all I have to do is take this script then and pipe it into the binary, and it gets my test flag. And we can see that if I take this to the netcat port, that it works as well, which is perfectly fine. It's just a bit cleaner if you print less white space. So I've also written a second script which does this in 2 writes just to print a little bit less white space, which is the solve.py here, which gets the GOT address for exit, the 804A02C, and then an address adjacent to that such that it's going to be writing the second least significant byte of the GOT address in its least significant byte, and then package that into a password using struct.pack as an unsigned integer in little endian. And then we do 2 writes where we do %hhn, which halves the halving of how many bytes %n writes, so 1 byte, because 4 divided by 2 twice is 1. Then we write the 0x13 as 19 in decimal, and then overflow that, which is however many, and then the 0x87 plus overflowing that through 255, so that the least significant byte of what this is going to write is 87, and we do 2 writes, and then enter password again, and it's good to go. So if I do that, it'll work on my machine, and we got my test flag. And then if I take this into the actual problem, prints a lot less white space and gets the answer. Well, there you have it. That's about it for this video. If you liked it, feel free to hit that button. If you didn't, you can hit that one too. Go ahead and subscribe if you want to see more cool CTF write-ups and crazy projects. See you next time.